Good morning to all. Today we are going to study about heat and mass transfer subject, and the topic is radiation shield, and I am A. Shankaranarayanamurthy from the Department of Mechanical Engineering from Kamaraj College of Engineering Technology. First of all, we want to know what is a radiation shield. A radiation shield is a thing that protects us from the overheat. That is, a heat shield is used to protect the components and the personnel who are working in a power plants, specifically in a thermal power plant or a nuclear power plant, where the heat exhausted will be very much high. That is, it will be around 1000 to 1200 degrees Celsius. So a person cannot stand or withstand the heat. So radiation shield is a must in such conditions. And the functions of the radiation shields are, it will be preventing the overheating of the nearby equipments. It will be protecting the workers from the exposure of the highest amount of heat, and it also improves the efficiency of the components. And now let's go and see some problems in the radiation shield. One of the problems is emissivities of two large parallel plates maintained at 1073 Kelvin and 573 Kelvin, or 0.3 and 0.5 respectively, and we have to find out the net radiant heat exchange per square meter for these plates, and also we have to find out the percentage reduction in heat transfer if a polished aluminum shield is placed in between the two plates which has an emissivity of 0.06, and also we have to find out the temperature of the shield. So let's move on to the problem. Let's move on to the solution. First of all, there is the T1, that is the temperature of the first shield is given as 1073 Kelvin, and temperature of the second shield is given as 573 Kelvin, and the emissivity of the first shield is, the emissivity of the first shield is 0.3 and emissivity of the second shield is 0.5, that is 0.3, and the emissivity of the second shield is 0.5. Let's make a small diagram so that we can understand it clearly. And these are the two parallel plates. This is one and this is two. It has a temperature of 1073 Kelvin, and this has a temperature of 573 Kelvin, and it has emissivity of 0.3 and emissivity of 0.5. So to find out the net radiant heat exchange between these two plates, we have a formula, that is Q1 to 2 will be equal to epsilon bar sigma A T1 power 4 minus T2 power 4. Here the epsilon bar, you have to calculate the epsilon bar individually, that is 1 by epsilon 1 plus 1 by epsilon 2 minus 1. So let's move on. So the Q12 will be equal to 1 the whole divided by 1 by epsilon 1 is 0.3 and epsilon 2 is 0.5 minus 1 into sigma, which is constant value 5.67 into 10 to the power minus 8, that is Stephen Boltzmann constant, and area, since it is given as an unit area, we can have it this side, and into the temperature, we have to remember one thing, the temperature should be always substituted in Kelvin only. And the Q12 per area will be, answer will be coming, it has 15,880 watt per meter square. So the net radiant heat exchange between Q12, first of these two parallel plates, will be 15,880 watt per meter square. Next we will be seeing when an radiation shield of aluminum, polished aluminum of emissivity 0.06 is introduced between these two plates, parallel plates. So now the diagram will be changed slightly. This will be T1 1073 as usual, and epsilon 1 0.3, and a shield of aluminum shield is placed in between this, and this will be 1 and this will be 2, and the shield will be having a number of 3, and the shield's emissivity is 0.06, and T2 573 Kelvin and epsilon 2 0.5. And now when we have to solve this with the shield, so Q13, that is a net radiant heat exchange between 1 to 3, and also from Q3 to 2 will be equal. The net radiant heat exchange between the parallel plate 1 to the aluminum radiation shield 3 and the radiation shield 3 to the parallel plate 2 will be equal. So, Q13 will be equal to Q32. So, the same formula applies here too. So, 1 by epsilon 1 plus 1 by epsilon 3 minus 1 into sigma value 5.67 10 to the power minus 8 into T1 power 4 minus T3 power 4 will be equal to 1 by epsilon 3 plus 1 by epsilon 2 minus 1 into 5.67 10 to the power minus 8 into T3 power 4 minus T2 power 4. So, when we substitute all the values, we can easily find out the T3 value, that is 1 by epsilon 1 is 0.3 plus 1 by 0.06 minus 1 into 5.67 10 to the power minus 8 into 1073 power 4 minus T3 power 4 will be equal to 1 the whole divided by 1 by 0.06 plus 1 by 0.5 minus 1 into 5.67 10 to the power minus 8 into T3 is unknown and T2 is 573 Kelvin to the power 4. So, when we substitute, when we solve this equation, the T3 value will be almost 911.8 Kelvin. This is what will the T3 value will be. So, for what we have to find out is the net radiant heat exchange per square meter for these plates, that is for parallel plate 1 and 2 we have already found out, and next we have to find out the percentage reduction in heat transfer when a polished aluminum shield of emissivity 0.06 is placed between them, and also find the temperature of the shield. We have to find out the temperature of the shield, that is 911.8. Now we have to find out the percentage reduction. The percentage reduction will be before that we have to find out the Q32 or Q13, which will be equal to 1 the whole divided by 1 by epsilon 1 plus 1 by epsilon 3 minus 1 into 5.67 10 to the power minus 8 into, that is T1 is 1073 power 4 minus 911.4 to the power 4. So, Q32 will be equal to 1.89 into 10 to the power 3 watt per meter square. So, this is a Q32. So, now we have to find out the percentage in reduction of heat, which will be equal to Q12, that is without radiation shield, minus Q32 or 13 with radiation shield divided by Q12 into 100. So, that will be coming to 15,880 minus 1.89 10 to the power 3, the whole divided by 1.89 10 to the power 3, that will be coming to 88.8%. This is the answer for the problem. Thank you.